It's okay now. So we will start the last session of this summer school. I mean, it will be given by the organizers and also the speakers. And the first one is Florian, Dr. Florian Brünig, and then the second speaker will be Dr. Miguel Gallegos, who are postdocs at the University of Luxembourg, working in the group of Alexander. Okay, Florian.
Okay, yeah. Welcome also from my side to this morning session where we will talk about, let's say, the current ongoing developments in this, around solar happening here in Luxembourg. So, as you already know, probably from yesterday's talk, our main workhorse is really the solar model, which was jointly developed by Adil and Tom from the Technical University in Berlin, so from Klaus Robert Müller's group, formerly. And Adil showed to you yesterday already some preview, basically, of the recent improvements of this solar model version 2, where there's like a few architectural changes, and very importantly, of course, this data set has been increased significantly. At the heart of the model sits still this Socrates neural network developed in Berlin, which is really comparatively small but very efficient architecture. And overall, this efficient network with the efficient implementation in JAX make this a very competitively performing model, specifically in terms of speed and memory, so system size. I also want to remind you of one of the in-house data sets that was recently developed, also shown by Adil yesterday, which is the Q-cell data set jointly developed by Adil and Sergio from the group. And I just mentioned that here again because I think in conjunction the efficient solar model and the Q-cell data set really sets the scope of applications that we are aiming for predominantly, which are biomolecular simulations. So the idea here is that biomolecular chemistry space is comparably small and comparably simple. So there's a lot of recurring chemical motifs that can be learned efficiently by these models. And the complexity of biomolecular systems really comes more from the system sizes and timescales that need to be addressed. And like 10 to 100K atoms and simulation timescales of at least of more than a nanosecond are really like systems and applications that we are dealing with on a daily basis. The group now is a solar model. Also, the complexity comes, of course, from ambient conditions. So we need thermostats, thermostats, and everything happens in the liquid phase, which, of course, induces significant disorder. So we have really a sampling problem of diverse conformations, which are some of them rarely visited. So I think for these systems, it's pretty clear that in addition to our commonly shown two-dimensional plane of computational cost versus physical fidelity, where it has usually shown in these kind of talks, it's usually shown that machine learned potentials kind of break the trends that were previously set by conventional quantum chemistry methods. We can maybe add another axis, which may not be orthogonal, but which comprises the sampling capacity.
You need to press once more because this one lags a bit.
I don't know. Oh, okay, good. Bit slow. Strange. And along this axis, we have also very competitive methods, not from quantum chemistry, but really like established methods like empirical force fields, which are very successful for biomolecular simulations. They are much smaller, and so they, of course, can perform much better in terms of sampling. So to compete with these established methods, we have a few options. Of course, we have to aim to make our ML force fields smaller, yeah, in terms of size. We have to distill them. We have to build the right data sets to compete with these force fields. We have to also adapt our sampling methods, and some of this has also been shown in the workshop already on Monday by Stefan, for example, that these sampling methods can also be accelerated and will be accelerated with ML, for example, in accelerated MD techniques or also ML-based enhanced sampling methods. And in the end, of course, implementations also offer really huge performance gains that can be used, especially when moving to modern hardware architectures like GPUs that have been shown to be very successful for machine learning, and this can also be leveraged more and more to address the sampling problem for biomolecular systems. So I think this would set the scope for a few of the applications and methods that I will show now in the following slides and also afterwards. So the first topic I want to address are chemical reactions, which are the focus of Eugene Monman from our group, who is also sitting here in the audience, so you can also address him directly after the talk. And yeah, so one advantage are that clearly over classical force fields is that machine learned force fields are reactive, so we are not bound to a fixed molecular topology. Yeah, bonds can break. However, these bonds rarely break, the barriers are fairly high, so naive sampling would really take a long time and be very expensive. And so Eugene interfaced SOLAR with the HiSages enhanced sampling library, which really is a very modern, implements very modern enhanced sampling algorithm, and importantly, it's natively implemented in JAX-MD, which is the same MD driver that is SOLAR is built on, and this really enables very efficient enhanced sampling simulation. So Eugene looks at protonation at equilibria, so peak AA values of molecules, and in these setups he looks at 25 angstrom boxes of water, so close to 1,000 molecules at 300 Kelvin, and performs around 50 nanoseconds of sampling with this adaptive bias, of course. So a quite modern sampling method. And trajectories would then look like this, where we see here this carboxylic group can be protonated on either of the oxygens during this course of the simulation. We see that this potential energy landscape is sampled well, and importantly also we are not stuck in the local minima for extended times. And then, of course, also very impressively, these converged simulations get very close to the experimentally well-characterized free energy difference for this molecule. Yeah, now you can see well the protonation of the carboxylic. So these simulations are done in water, but water is of course not the only solvent that is interesting for biomolecular simulations. So we also went on to benchmark organic solvents, and we benchmarked them directly against macroscopic experimental values. So most importantly, of course, the density, and we find with solar version 2 that we get within 5% error of experimental densities here on a diverse set of 16 organic solvents, which are quite widely used and common solvents, and also cover diverse subgroups. We here already excel the performance of OPLS, which is widely regarded to be one of the best classical empirical force fields for model observation. When looking at diffusion constant, the results are still significantly worse. So with solar we get to 25% error, which, however, is on the same order of the errors of the OPLS force field and amber, so the gap force field, actually performs still significantly worse. So this really shows that such long time-scale dynamic properties are actually still challenging to get correct initial, but from an atomistic on still definition-based machine learning force field. Having now benchmarked organic these different solvents, we can come to the next point and look.
Florian, can you elaborate on what is potentially missing? Is it only the force field?
I mean, one aspect would probably also be nuclear quantum effects. Yes, but yeah, I would say.
It's not just the force field, right? There could be many other things which are still missing.
Right, but I think the grand challenge is really also that, long-range effects, of course, the accurate modeling of them is still a challenge for force fields.
Must the reference DFT here?
The reference is experimental.
No, for the version 2 of Solar.
Well, so as you remember from Adil's talk yesterday, it's basically multi-head trained. So it's trained actually on the embeddings are trained on multi-reference. So on
For these quantities, which head do you use?
this is the final head, which is then again fine-tuned on PV0.
PV0 plus.
No, this head is fine-tuned on all of the data. So we just first train with 2 separate heads, and then we have one final head for all the simulations. And this is omega B97 MWB and dash V and PB0 plus MBD data that we have. So for these 2 levels of view.
Thanks, Adil. Okay, so we can now look at solver-to-chromic effects. So, so the response of certain molecular properties when placed in different solvents. And some of that was already hinted yesterday, also in the hands-on session. So a very widely known and studied solver-to-chromic effect is the shifting of vibrational bands in different solvent environments. As you can see here, for example, experiments of this carbonyl vibration, which are shown to shift significantly here by 50 wave numbers when placed in different solvent environments. So the origin of this band shifting is generally understood, usually from the anharmonicity of the bond potential, which is, and this bond is stretched due to the solvent environment. So when we are operating at a different point on this anharmonic potential surface, the effective curvature is slightly reduced, which decreases the frequency and causes shifting of the vibration. So performing these calculations of these frequencies in explicit solvent environments is failing clearly for empirical force fields, and this is mainly due to the fact that they have harmonic bonds. And since they don't encode this anharmonicity, they cannot a basic amber simulation, where now this spectrum is actually calculated from the full dynamics using the autocorrelation function, cannot shift when placed in different solvent environments. So the common approach to fix classical force fields here would be to basically make this bond potential anharmonic, which can be done fitted with respect to some reference, the same, so in this case again PV0 reference, which can then recover some of the shifts, but really not as good as a machine learned force field, which can really quite nicely quantitatively reproduce the experimental data. So there is here some remaining offset, which is largely addressed, or can be largely addressed to nuclear quantum effects, which I will talk about in a few slides also. A second example would be this nitrile vibrational bond, which is a much clearer failure mode for classical force fields, because when these are parametrized also anharmonically, and here we have much stronger shifts because we are sitting at higher frequencies. So to illustrate that, I will just subtract here the vacuum baseline, so to say, yeah, to shift all these spectra here with respect to the experimental data. And there we can then barely see, because the shifts in the classical model are very small, that the trend here is not even qualitatively correct. So importantly, this water vibration, okay, colors are a bit difficult to see here. So this is the water peak, which is actually shifted to the right, so to higher frequencies of the vacuum reference, and in this corrected classical force field, and it is very much shifted to the left. Yeah. So solar, in fact, here gets all the qualitative trends and even quantitative quite good agreement with the experimental data when correcting for this baseline due to nuclear quantum effects. So how can nuclear quantum effects be addressed? So these effects comprise 0-point effects, delocalization, and tunneling effects, and in generally they become stronger for higher frequencies at lower temperatures. Yeah. So this is like a common illustration which shows here the position variance of the classical versus the quantum harmonic oscillator. I show here on the surface plot of temperature over frequency here the positions of the well-known frequencies of the water spectrum. So at low frequencies in the terahertz regime, the H1 vibration and the vibrations here, classical and quantum models are very close together, but when we move up to higher frequencies, so already at the bending vibration here at around 1600 wave numbers, there's significant differences between the classical and the quantum model, which is exactly the regime where these simulations that I showed on the previous slides and the experiments were done, and then at higher frequencies above 3000 in the stretching regime, these deviations become even much stronger, which is also well reproduced in simulations. So these quantum effects can be addressed within the Feynman path integral formalism, where basically quantum statistics are approximated by, instead of simulating a single classical nucleus, this nucleus is expanded in a ring polymer of replica simulations, where the same beats are always coupled by a harmonic spring. And these simulations run together, this ensemble of replica simulations then reproduces approximately quantum statistics. So for bond vibrations, this equally means that due to this 0-point offsets, the bonds are slightly stretched and the frequencies are quite generally shifted to lower wave numbers, so closer to the experiments as we saw. So here, this works for classical simulations and also for this condensed phase simulations as an example of which, this is also here the CO carbon vibration. So these simulations are commonly done in IPI, which is really the reference package, I would say, for performing simulations. And IPI is a quite flexible modular ME engine, which is interfaced through ASE. Thereby, it is, however, CPU-based and has significant communication overhead. And this cost of these simulations can become really significant when you have to simulate 10 to 100 replicas simulations, which is what is required here in this regime of reproducing vibrational shift. So to address this, we ported the most important parts of this IPI package also to JAX in a compiled path integral molecular dynamics simulation loop with batched evaluation of the replicas beats, which performs then very efficiently, especially for small molecules, where we see that actually for a large number of beats up to 100, we really have very little small factor of additional cost. And yeah, for larger systems, of course, this degrades as we are quenching the GPUs, but we still perform here sublinear also for systems up to 1,000 atoms. Strange that this is like yeah, so multi-GPU evaluation is also very efficient, and this is because actually these replicas are very weakly coupled just by these classical potentials. So we can basically, and this is possible in JAX, efficiently evaluate part of the beats on different GPUs, which is called sharding. So we are sharding basically these evaluations along the replica beat axis, and yeah, this performs near ideal and when we're scaling across different GPUs for larger systems. Of course, for smaller systems, there's still some communication. When we now compare the overall performance to IPy, we find that we get gains here from about 5 to 50-fold, so really quite nice performance gains that should enable really a lot more efficient path integral simulations. So we hope that we can make this happen. Package also publicly available very soon, and as it's JAX-based, we'll be able to run all kinds of JAX-based implementations of potentials. So I will just jump here to the last slide and say that we can also analyze the failure mode of the classical force fields by looking at the additional response that these machine learned force field carries, so this fluctuating charge response. And so in a classical force field that has fixed charges, we see that this is in fact sufficient for these carbonate vibrations, but in case of the nitrile vibration, actually this fixed charge model clearly fails, and adding charge responsive models, specifically the charge response here on the bonding atoms, increases is the root cause for the frequency shifts in photonic environments in one. And with that, I would like to pass over then to my colleague again.